Welcome to today's webinar. The topic today is analysis of multi-layer surfaces and application of building models in RFEM 6. My name is Andreas Hörold. I'm responsible for marketing and public relations in the Dlubal software company. For instance, the Dlubal website, the German and English webinars, customer projects, etc. I've been working for the company for 12 years now. I will be the moderator today. The presentation will be done by Bastian Kuhn, but he can introduce himself.
Hi, thanks, Andreas. My name is Bastian Kuhn. I'm responsible for the customer support and the development of the add-ons related to timber design and with the building model, what we will show you today. I'm in the company in the beginning of next year. It's been 15 years since that I'm working here.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. You have the possibility to ask questions via the control panel on the right side of your screen. I will answer you. If you don't get an answer during the webinar because there are too many, you will get an email afterwards. The other way is to watch the entire webinar and then email your questions to info@dlubal.com. To the agenda today, at first, Bastian will define multi-layer laminate surfaces. Then he considers the stiffness reduction for deep beams and panels subjecting to bending. Then he will turn to the add-on building model. The third point is determination of loads for bracings on the building model and the calculation of story center for dynamic analysis. Okay, then I hand over the screen to Bastian. Okay, Bastian, it's your turn.
All right, hold on, I have to choose the right monitor. Okay, there you see it. This is our homepage with what we will start today. I will go afterwards directly into the program and show you everything there, but just 2 points that are maybe important I want to mention on the start. What I'm gonna model today is can be a little bit compared to the 18-story mass timber hybrid structure student residence in Canada. It's quite an older building already because it has been assembled in 2016, but still a very nice structure where I can show you the advantages of the add-on multi-layer surface and the other add-on building model. When I'm in the webinar, I don't want to go into many detailed analysis or explanations in the webinar because we just have no time for that, and it's just some points I have to consider and to define there. But just for your information, for example, we will reduce the reduction factors K33 and K88. Here it's for the old add-on RF Laminate, but we will do it also in the multi-layer surface add-on today. And here on our homepage, you have to all these topics and all these values, what I will define there today, and when we will also design the connections and the stiffeners in the structure. We also have articles on our homepage where you can read the theory behind that. Okay, as I remarked it already, the project is quite old or a little bit older. 6 years is not that old for a building, I think. But just last week, I saw a project here developed in Germany, in Hamburg. It's quite a similar building, considering the height, than the building in Vancouver. So it's also 53 meters, I think. And 18 stories. So, and they're right at this spot where you can see my mouse. That's where they are in the assembling process right now. So buildings like this are spread all over the world, and that's the reason why we want to model or want to show how to model this with our software. First of all, that's the new RFEM 6, and we will define a new model there, and we will call it 2D, just to keep it similar to the models that you can download after the webinar in the link that we will show you via send you via email. Type of model, we will choose 3D as an add-on. For the start, we will only consider the add-on multi-layer surfaces, e.g. laminate or CLT, but there is nearly all materials are possible in there. For example, concrete hybrid structures and GFK or whatever. We will not consider the load wizard, and we will also do not a pure design. The design later on, for example, for CLT in future will be done for CLT in timber design. And yeah, if we have a concrete hybrid structure, it will be done in concrete and so on. As a standard, as we did not have many add-ons for the design activated, we also do not have many standards to assign. But what I will do is I will generate the load introduction or the combination according a timber standard. When you are in another country than Europe, you can see for nearly all kind of countries, we offer special combinations for timber. So that's here Europe, here it's America, it's Canada, Switzerland, and so on. The main difference, if you compare the pure Eurocode with the Eurocode with timber, is that when you go to the editor here, you can activate a so-called deformation coefficient. That's nearly the same in all the countries. And what we do here is that we increase the loading in order to regard creeping of the timber material. That's how it's nearly done in all the countries that I just mentioned. That's the theory behind it. It's also possible to do this on the stiffness side, because creeping is actually not an increasing of loading, but it's an additional deformation that you need to regard. So for a nonlinear system, this approach is not always sufficient, but it's a simpler approach. And for the structure, what we will build here today, it's good enough. And I just want to show you how to regard it. Okay, then we activate the structure, and we will define the surface. Here you can define a new rectangular surface, and you see there already that there are already layers assigned, but we want to have a new thickness in here. Maybe I can actually delete. Wait, I will just do it in the dialog itself. Just that we have a pure empty dialog there, and sections we also don't need. Come on, this and also this other one. It was just saved from the previous project. So now we have an empty project, and we can say, okay, create a new thickness. And here you have the thickness type uniform. And here, so that I activated the add-on multi-layer surface, in the basics, you have here an additional thickness type layers. And when you go in here, you see on the bottom, you have the option to reduce stiffnesses. I will show that after I defined the layers. Here you can define a thickness type, for example, directly. In the future, we will also implement solids into the layer database. Then there will also be contacts possible to be defined here. But right now, it's only possible to define directly. And here we say, okay, I'm choosing a new material, and we go to our new material database. The material model I will choose as orthotropic linear elastic for surfaces. theory behind that you can read, as I mentioned, on our homepage. Just for your information, orthotropic means a higher stiffness in EX than in EY direction. And then we go to the material database. We are choosing the region Europe and material type timber. And here you can see that we have already cross-laminated timber. And we are right now implementing all the producers here. In your customer version, you have the companies Binderholz and Haslacher from Europe. But Binderholz we will also implement soon for the American market. And we will implement soon very many more producers here. Stora Enso is on the way, and so on. So this list is going to be filled in the future. And when you choose it and activate it, you can see actually in the material values that when you choose the CLT material, you have here more characteristic strengths. So you see you have here netto and torsional shear stiffnesses, and that's what we are for the design in the timber design add-on will use in the future. Maybe we compare that with an ordinary solid timber, let's say C24. There you see we do not have this dividing into several shear strengths. Okay, and now we choose the normal ordinary C24 material. We make it actually user-defined for our approach because we say in the Y direction we do not want to regard any stiffness, because a CLT, what we are going to build here, has always, because of the cracks in due to the dry process, it has no stiffness in the secondary direction. That's why you define it here with 0. Because of the layers, you still have a stiffness in Y direction. That's one of the advantages of CLT, and that's why you actually are implementing. So it's not 0 for the whole plate. It's only in the one layer what we are defining here. Okay, that's again probably too much theory for now. Here we are using 10% of the shear modulus because that's just determined by the standard. Okay, then it's defined, and I'm defining a thickness of 35 millimeters, and you see here that we have a rotation angle that you can define any angle you want, let's say 45 degrees or whatever, 90 and so on. But we will use for the first layer a rotation of 0 degree. Okay, then we want a 5-layered plate. We do this 5 times. And for the material, I will actually define just the C24 again, just to have it in a different color. It just makes sense later on in the rendering. I will show you that directly, but in the end, it's actually the same material. It should also be user-defined and have this 0 stiffness in this direction. Okay, 35. And then here we will choose this again and this there. And so now we have the orientation of the top layer 0 degree and the bottom layer, the middle layer 90 degrees. That's the usual setup of such a CLT. And now, because I showed you the FAQ, because of the timber behavior, you need to reduce the stiffness, mainly for the values K33 and K88. These are usual values, what you will normally have. We can take this here, so 0.67 and 0.6 for K33 and K88. Sometimes customers are asking us about the shear correction factors. That's actually calculated by the software, but of course you can definitely also define your own modifications here if you want. But yeah, as I said, there's also an FAQ where this is explained in detail. Okay, now the thickness is defined and we can start the modeling process. Go into that direction, keep the origin. And so the building has a length of 55 meters. and each plate should have a width of 3.5 meters. Therefore, we will edit the node and say, okay, here we want 3.5. Everything bigger than this, it's just not possible to be transported to the job site. The orientation I wanted to show you as well. So you see here when you go to surfaces, surface axis system. So you see 0 degree is now our axis system. So that's the correct angle we have defined here. And also the rendering I wanted to show you. The reason why I chose a different color for the second surface. So that's here when we took this. You do not see that much, but when you go to colors of rendered object, you see now that you can see the, hold on, we need to go, to material. And now you can see the different colors over the layers. Oh, so now it's better to see, I think. Okay. Yeah, that was one of the reasons why I chose this different material. Okay, then we need to copy this point 3 times via our option move copy 3 times and do it in Y direction, about 3.5 meters. That's now a little bit of a modeling process. Wait, I will actually switch off the axis system and I will divide the top layer, the top surface here by 3 nodes, just intermediate, in order to define my stiffening elements of the stairs in the structure. So, and right here. So, and on the origin, we want the stairs to be started by a value of 12 meters here, and on the second node by 18 meters, so it's 6 meter long, and the third it will be by 37 meters. So that's it. Then we will just copy this nodes here because we want to have the stairs a little bit longer. We do 1 copy and it should be minus 1.5 meter in the Y direction. And then we have there, and now we define the outlines of the stairs, and then just will also copy this to the right side. Oopsala. So, okay, then we will just cut that. So, and via right click on the surface, divide the surface by the intersections, by the intersecting lines. So, and now we have the kernel there. So there you can see it probably better in the rendering. So, and what else are we going to do? We deleted the lines. Now we will, we have the facade of the structure is 40 centimeters on the outside, but the structure itself is more on the inside. Therefore, we will copy the outer line by 1 copy and do this by 40 centimeters in this direction. Oh, wait, I made actually, no, I did not make a mistake because it's not intersecting. Yeah, it works fine. Okay, so the structure is already there. Wait, take a look on my sheet of paper and copy also this outer line 1 more time, about 13.2 meter. And now I have to divide also this inner lines, because I want support on every part of this, every 3 or 4 meters in this structure. And therefore, I want to activate the line orientation in here. And it's important that all lines are in the same direction. And you see this one is not. And therefore, I will change it, the line orientation, via reverse line orientation. And now I can select them all and divide them all, of course. So this, and divide the line by a distance at the end of 50 centimeters, and then via you know, in RFEM 6 we have a new function. Via shift you can deselect, and via control you can select. You see it on the mouse, probably, hopefully you see it on the mouse, because there's a plus and a minus. Either way, you take one of those buttons. Okay, then on distance on start, it will be 50 centimeters. All right. Then we will divide this by a number of intermediate nodes of 11. But very important, before we do this, we will create line or nodes without dividing the line. That's a function that has been developed quite a lot in RFEM 6. And if you are coming from RFEM 5, it's not so important to use the set of members so much more, because this function is something that will really help you a lot. This line here, I actually could have deleted from the side. It's not so important, but just to keep the structure a little bit clearer, I could have deleted it, and this one as well. And now we have to divide the lines on this kernels here as well. So then we will divide it there and divide it there. And now we will just, copy this line, this node and this node, because this is where our foundation or our columns are placed then in the next step. Right, move copy, and we do one copy, and by again minus 3.1 in the y direction, and then it's there. All right, so that's now fine to me. I think anything I should have forgotten, maybe this one, and this one we can also divide. It's also not that much important. Come on. Yeah, maybe there. Is there a node? This one we can delete. Yeah, here. It's not important. And the line orientation we do not need anymore. And here and here. So these nodes we can all just grab. Oh no, we should have also deleted this one. Here, here, and oh, that's not so good, because we should have divided it before. Okay, so now it should work. Man, so okay, that's just now just cosmetics, but it helps because of this building, of this 2D structure. We will create the 3D building afterwards. Okay, that's all done. And now we can define the line hinges, and that's a very cool new function in RFEM 6, because if you remember RFEM 5, it was quite a pity to define line hinges, and that has been developed very nicely, in my opinion. Therefore, we go, that's the same as in RFEM 5, insert types for line hinges dialog box. But when you are in here, you have on the right side assign to surface and lines. So it automatically assigns the lines to the surface that you need, and you do not need to click on the surface, say okay, and go back and again, and then you have hundreds of line hinges. We will just create one line hinge for the whole connection of the CLT plates. You see, you know that the first CLT plates need to have a slippery compared to the second one, and so on. So that cannot be bending stiff for the rotation. We also will define the slip of UX and UY. Theory behind that, as I said, is explained in the FAQs. It's quite a low stiffness that I define. It's probably something, a small nail every 40 centimeters. That's what you can compare actually the spring constant with. Rotational constant in the history, we used to define their value of 0 or near 0, but newer approaches from the universities show that there is also quite a higher stiffness possible. Maybe not in compared to the translational stiffness, but it can be higher than 0. That's just what the new approaches give us. So, and now I made a mistake because I ended the command. That was, yeah, you know, that's so you stay in this window, and then you say, okay, assign to lines and surface, and then you choose the surface, and now you choose the lines. That is not so so terrific, but now when you press OK, you can select it again and do not have to define the whole hinge again. So that's something that's yeah, quite a new and cool functionality. So here, okay, and now the next one, this, and then that's it. Okay, this and this and this. We will also define those hinges. So now they are there, you see. They may be a little bit small, therefore we have this new function you also can have for supports, for any kind of graphic objects. You can increase the size of them, especially for this webinar, it's quite important. On the stiffening element where the stairs are running, which is made from concrete, for the 3D building, we also need this line hinges, but for the 2D building, we do not need that. And there we will define line supports, but the line supports have actually the same stiffness than the line hinges have. So I define it here in the same way. And of course, I want the support in that direction. That's something what we sure want. Hold on, I made a small mistake. And the coordinate system should be oriented in local direction. Okay, then I can define them, and now they are assigned with a slip. Tuck. Oh, that did not work. This one, this one, this one, and this one. Okay, so now the supports are there, and we can take care about the nodal supports that are in the 3D building, the columns. They should only bear load in Z direction, not X and Y. Right, right, right. So, and then we go there. This, and zoom a little bit in. This, and this, and this. Okay. Now it's supported, and we have to take care about the load. The first load case self-weight is already assigned. I will also define an additional self-weight load about 1 kilonewton per square meter over the whole structure. Say okay, and then we have it there. And we will now also define live loads, but just on the CLT plates 1, 2, 3, 4, not in the X direction. When you do a practical example of this, you definitely should have done it also in the X direction, not only in the Y direction. But for our endeavors here, this will be okay. So we define 4 more live load cases with a load duration class of medium term, and we will define 1 new load case for wind load. What we also will define there, say okay, and then go to the load case 2 and define this in every field. We will define a live load of 1.5 kilonewton per meter. Again, we're using the same intelligence as in the line hinge. Apply a next, and then we go to the load case 3, do the same there, assign it. So the logic or the modeling process in RFEM 6 can be speed up quite a lot, because you do not need to leave the dialogues or not so often anymore than you needed to do it in RFEM 5. That's something I wanted to show you with this process. Okay, here you need more than one surface. Okay, say okay, because now we're leaving this dialog because I want to take a look if I did everything correct. So load case 5, 4, 3, 2, that looks good. And in the load case 6, we can, if we want to define a line load with a value, I don't know honestly, load direction, we take 1 kilonewton per meter and take the y direction, and then say okay here on the outer line, okay, and then it's there. So that works the same as in RFEM 5. That was the old traditional way. So we did both options. Okay, now combination, and we can do the or start the analyzing or design process. Take a short look to load cases and combination. The combination wizard is on. Here, design situation, I will just do ultimate limit state and quasi-permanent in order to regard a creeping. You see there's the factor that I showed you on the start. Here we will do a combination according first order theory, because we are in a 2D position and we did not define any kind of imperfections and so on. And because of this, design combinations are done. They can be compared to the old envelope of result combinations. It's just that they are done automatically and can be used directly for the design process. Now, when we calculate, for example, the first design situations with all the with all the combinations inside, we can take a look how much there are. So 47. And you see that all the combinations are calculated in one step. If you compare this to RFEM 5, there was always every combination calculated after the other. So the speeding up process for such a structure related to the combinations can be quite significant in RFEM 6. Okay, now we have the results. First of all, okay, deformations, that is in this 2D structure, maybe not, I mean, it's in information, but for example, if we look for the load case 6, the wind load, it can maybe be a little bit more interesting to see the results just in horizontal direction. And so you see it's like, yeah, bended in this way into the plane area. When we then look for the supports, you see that you have the support forces. You need to connect via connectors to the concrete kernel of your structure. Also, the plates inside each other need to be connected, or as we defined the slip, they are connected via screws or something like this. And you can also design them in here, and therefore you go to in the result navigator, releases, line hinges, forces. Actually, what you want to verify in there is the normal force inside. So you see the maximum you have, yeah, right here in the middle. That's logic, I would say, with a value of 0.4 kilonewton per meter. That needs to be yeah, built by connectors, screws, or whatever you are defining there. And now if you want to know the sum of force that is in there, you can do this also via right click result diagram. Hold on, we can go maybe directly onto the line. It makes maybe more sense. There are now, you see, quite long, quite a lot of values that can be a little bit confusing. What's the reason for this? The reason is that it's showing you the forces for all the lines attaching to the surface. And so for our endeavors, when we look in here, we definitely want it just for the line 43 on the surface 5. So, and then it looks quite better, I think. You also already have a length of 54 meters. The reason for this is that we reduced it on the by 50 centimeters on the start and end. And now, as I said, we want to have not deformation. That's not our interest. Also not local deformation. And also not whatever that value is here. We want the line hinge. Just let me take a look. The normal force in the line hinge. Hold on. Therefore, I choose actually the wrong result diagram. I need to check this one. So then this, not this, but there is already. You see, there's the normal force in line hinge because I activated in the outside. So, and now you can see how can I get, let's say, the whole force that's from the start of 0 meters to 50 meters, let's say 60 meter 50. It's possible to also take edit smooth ranges. I will just do that for 0 to 16.5 and maybe from 16.5 to, yeah, it doesn't have to be, let's say here 25 and okay, and we want a constant value. And then you can see, okay, 6 kilonewton is the force that I need to bear by the screws, and that gives me an overall value of 0.374 kilonewton per meter. So that's the force that I need to transfer through the building. So that's the connection design we did already, or how it can be done. All these informations can be exported into Excel, and you can also yeah, get the results there and do your design process in there. And now we want to look also for the stresses inside. So there, when you look for the top layer, that's the top layer we are looking in here, and just the basic stress sigma x in negative direction, but maybe not the load case 6. That's maybe not so interesting. Maybe we will take a look at here. That should probably give me the combination 5 should give me the highest moments over the columns. So, and you see here a value of here in the peaks in the singularity points of the columns of about 7.095 at the top of the surface. And if you go to the bottom of this layer, you have to change the origin. You see that there also you have the 7, and you can actually see how the stresses is changing there. Where you have a high stiffness, you have a stress in this direction, and where you have a low stiffness, you remember that we defined the stiffness in y direction there with nearly 0. You have, yeah, less stress. So that's for the bending stress. And of course we have also all the shear stresses. Let's say here that's the rolling shear. Okay, there's not a real rolling shear problematic inside here, only over the columns. That's where you need to verify that for sure. The punching of the CLT needs to be verified as well. Okay, that's CLT. We will now start with the 3D building. Therefore, as I said, we have to, at first I will switch off the load cases and combination wizard, and I will keep my existing combinations, which is okay for me and also okay. And then I said we need, on the 2D, we need to have also a slip of the CLT plates to the concrete kernel. Therefore, again, we just can go to types for lines, line hinges, and you see now we have just this one line hinge, and it's absolutely no problem to just go inside here and say, okay, this, and now I want to have a slip on this line as well, and then I take this surface, this, and this surface with this line, and of course this. It's just, it's still a little bit of selections you need to do, but it's way less than it has been in RFEM 5. Okay, and now it's there. What else do we need? We need the concrete kernel. Therefore, we will copy this line here, wire move copy, create one copy, not in Y direction, but in Z direction, of a value of minus 2.9 meter. And we will, first of all, copy including loading. That's important for our load cases later on, not yet. But the thing what I want to show you here is step links. And there you can link lines within surface. We need to define a template for this, not a layer, because that's the concrete kernel that we defined, so it has a uniform type. And we will go in here and say concrete and take it maybe a little bit higher strength of C30, C37. Maybe the thickness on the bottom of the 18 stories building should be thicker, but for this webinar, I will just keep it constant. In here, say, okay, now this is my template, and then I say, okay, and I have the surface generated, and I will now just copy this one and this one, oops, here to the outer line, and then just draw this surfaces here in the other direction. Yeah, also this can be copied, but yeah, as I'm just in the drag and drop process, I will just define it in here, and okay. So now it's there. The first concrete kernel of the outsides, this one have to be activated. So, and so those, now then we will, did I activate all of them? Yeah, I think. So then we go in that direction and we'll activate the all the nodal supports. We are, again, I'm using the control function for this because it's quite a nice function. If you are again coming from RFEM 6, RFEM 5, this process, what I'm doing right now, would not really work in RFEM 5 because now I can only activate additional objects and still keep the surfaces selected. So this one I missed here. This one we need, this, and this. Okay, that I did not grab, but everything else I have. And now I can just go in here and say again, move copy. Now I'm copying all the stories, 18 stories on the bottom, and in the, so copy including loading is now important. And now the step links, we will not copy the surface, but we will use a template of the members inside. In the first floor of the structure is made from concrete, but all the others are made from timber. That's why we choose as a template now the timber section in here. We choose a massive section with a value of 35 by 30, oops, not 3 meter 50, but 35 centimeters. And as a stiffness, we will use timber and a little bit better material from timber for glue laminated timber, GL28C. All right. Hinges we will also define because we are the beams, the timber beams cannot be connected without a hinge usually. Just a moment rotational we will give the freedom, and we do it the same on start and end of it. So that's it, and then we say okay. Wait a few seconds, hopefully. And then the structure is there. Maybe put the rendering on. So that looks quite good to me. The top story, okay, here, that's the reason why I activated before. That can be deleted now, and now we have the concrete kernel and all the CLT plates on the other side. One part I have inside here, the supports in the upper levels I don't need. I can delete them via right click, nodal support, delete assignment. Now they are deleted, and in the bottom I can change them, the supports, because as I said, in the bottom I will have concrete columns, therefore the nodal supports can be changed to fixed supports. They may be now in this 3D structure a little bit less visible, and here again we also have this little range and can increase the size maybe a little bit. Okay, I will keep the nodal supports here on the bottom as they are, but the surface, the CLT surface on the bottom, they do not make any sense. Therefore, I will keep those surfaces in here and delete them. So now they are deleted. Now there is a problem with the load K6 because a line load needs a surface to what it is attached. Otherwise it will not work. Therefore I'm deleting the one load on the bottom. I could have, usually the wind load needs to look different. It needs to be higher on the top story than on the bottom areas. And I should have implemented here also a force that's attaching to the columns, but I think it's okay for this webinar. And then what else I need to do is to take these columns here and make them from concrete. So therefore I go members, edit, and section. I will use a new one, and that will be 40 centimeters by 40 centimeters. So a little bit bigger, but the horizontal force is not that low. I will take it just the same material than the kernel. The hinge at the end, I can then, at the start, actually, no. At the start, I have no hinge. At the end, I will probably have a hinge because there's a CLT plate on top. Yeah, that's how it should work. So you see, that's this point, and maybe we will just take a short look to the load K6 because this is our horizontal deformation. And then we go to the building model. That's what we will to do, just to show you the deformation. I hope we will have it soon. I don't know, as there a surface inside, usually it should go a little bit quicker. I mean, it's not that smaller structure now. Maybe I can take the chance and take a look if we have any open questions. No, not the case, but the result is already there, so we're fine with this. I hope. So, no, I clicked too quick. So there it is. Okay, so we want the deformation. Just to take a look on the deformation in horizontal direction, which is the case for this load case 6 in here. So you see it's deformed in this area. But for such a structure, I think you all agree that it's quite big. In a 3D building, it's not so easy to analyze the structure and the results that are coming from it. And therefore, we developed the building model add-on. So we go into add-on and activate this building model. We say, okay, don't need to change anything else. And it looks now also quite similar to it was before. But now that we activated this add-on, you have here on the bottom a new entry building model. And then you say, okay, new building story. And then we say, okay, the bottom can be 0 and the top of the first story should be -29. You have here the option to show it also directly in the graphic, what the software is doing. So you see now we have a story we are just working in this story in here. You have several options. You can all read that in the online manual of this add-on. Just for your explanation, your rigid diaphragm, I will show you probably right in the first story because then it's possible to see it. Rigid diaphragm is something made for concrete structures where everything is bending stiff on the moments. You see there's a center of the whole story. That's the first story of the building, and it's connected to all FE nodes. So that's something where what you would probably need for accidental torsion verification in the dynamic analysis. So that's the point you were always looking for. That's one of the advantages, not for our structure here, because we are defining timber. Therefore, we just choose nothing in here. And now we will define all the 18 stories. But as the first number is 0, we just need 17. Oh, again, I clicked too quick. I can get rid of those here. Yes, I want to delete them. And so you see now we can just walk through the whole story or the whole building per each story. Then we say okay. And now what I said it already, what the advantage is for the analysis and for the results is that you get additional masks and columns where you can get the force in every story, in every wall. You get a force that's transferred into the wall that you can read out. That's actually the theory behind this add-on building model. Okay, the load case 6 took quite a while in the 2D. It will probably not be quicker in the 3D building in here, I assume. It's also the GoToWebinar software that's a little bit taking the power from my machine, I think. But okay, now we have it. And now when you go to the result mask, come on. Yeah, so static analysis. Overview, you have now results per stories. That's the additional columns that you have. And you see, you have here the forces in each story very nicely to see that in every story you are attaching more or less 50 kilonewton on the story. You have a location of the resultant story forces. You have also in the view navigator automatically generated building visibilities or story visibilities that we can activate and just look for them. Probably makes sense to just look for one story in here. You have a location of a resultant story forces. So the point that I showed you with the rigid diaphragm, you also see the result, or you have a value of your resultant story in each force where you can attach it, and that you can define the deformation of each story you have. So you see on the top it deforms more than on the bottom, obviously. You have the center of the mass and the rigidity, and you also have the masses that are acting in your structure, and that I mentioned already. You have the forces in the shear walls. Oh wait, it did not activate my visibility. That would have been more impressive when we show that just for let's say the second story, the second floor. And it's also much more easy to see it then. So you see in here when we go to the bottom story, you have a very important value is that you have the force, the shear force that is in your shear wall inside. I mean, now it's from concrete, but if you assume that it's made from a timber frame wall, it's a very important information that you want to gain. Also, you can display this graphically. So when we say this is now the surface number 31, you can go in result sections in here, and then when you show story number 1, you also have maybe not for the deformation, because that's we do not want to see. Say we will only display this one by selected and related object. So, but you can see the resulting force also graphically via this screen in here for all the directions that you want to have. Okay, so that's the advantage of this add-on, what you can have. And additionally, what I did not show you today, you also have this mask center of mass and rigidity in the dynamic analysis. That where you can also use it directly in the dynamic add-on. Okay, thank you for your attention, and I give the word back to my colleague Andreas.
Okay, thank you, Bastian, for this nice presentation. Yeah, we recorded this webinar. I would like to show you where you can find the recording, but you will also get an email in the next days. Now, on our website, Dlubal.com, you can find under news and events the webinars. Yeah, all our webinars have been recorded. That's today's webinar. And if you click on it, you will find the recording here in the middle in the next days. And also you can find the provided models and you can download it. Yeah, just try it with your version, or if you don't have got RFEM 6, you can use the free trial version. Above on our website, you can click on that button and you will find the free trial version of RFEM 6, RSTARP 9, RSection, RWind, and so on. And the versions of RFEM 6 and RSTARP 9 contain all add-ons, and you can go step by step for this or through this webinar or to our other recorded webinars. Okay, that's also all from my side. Maybe a last hint: when you leave the webinar, there's a small survey. Just take the time. It takes only half a minute or 1 minute to answer some question or to score us. Just note the worst score is 1, the best score is 5. If you don't want to answer a question, just enter a minus or something like that. Okay, then thanks again, Bastian, for the presentation. Thank you for your attention. I wish all a nice rest of the day. Bye-bye.